Welcome to today's Explainer. Okay, I want you to picture this. You're standing on the floor of a drilling rig, miles out in the dead of night, and suddenly, every single light snaps off at once. I mean, total blackout. The massive diesel engines are completely dead, the pumps have stopped, and this eerie silence just falls over the entire rig. But you know, the dark isn't the real danger here. 10,000 feet below you, a bubble of high-pressure gas has just entered the wellbore, and it is racing up the hole straight toward the surface. So in this ticking clock scenario, you have roughly 30 seconds to slam the well shut. Because if you don't, that gas expands and violently unloads the well. It's a catastrophic blowout. But wait, you have absolutely no electricity. There are no hydraulic pumps running. Everything that normally drives the rig's heavy machinery is completely dead. So, what on earth is going to close those massive blowout preventer valves down in the cellar? Well, the answer actually lies in a heavy steel rack of bottles sitting quietly on the ground, totally independent of the rig's main power grid.
That unassuming rack of blue steel bottles is called the Accumulator, or as it's very commonly referred to out in the field, the CUMI unit. You can kind of think of it as the rig's ultimate heavy-duty emergency battery, but instead of storing electricity, it stores immense physical pressure. Its one and only job is to provide the raw hydraulic muscle needed to operate the blowout preventers, the BOPs, those huge safety valves stacked right on top of the well. It stores enough brute energy to close every single one of those valves and seal off the wellbore, even if the rig's main power fails completely.
All right, let's dive into how it actually stores that energy, because it's pretty fascinating. Inside each of those steel bottles is a thick rubber bladder, pre-filled with nitrogen gas at about 1,000 psi. Then, the rig's charge pumps force hydraulic fluid into the bottle right underneath that bladder. And here's the fundamental law of physics we're exploiting. Gas is squeezable, but liquid is definitely not. So as more and more liquid gets pumped in, that nitrogen gas just gets squashed down into a smaller and smaller space at the very top of the bottle.
Now, because that gas is being compressed so incredibly tightly, the pressure inside the entire bottle shoots up to a massive 3,000 psi. It's literally just sitting there, coiled and waiting. The instant you open a control valve, that highly compressed nitrogen acts exactly like a giant spring. It shoves the non-squeezable hydraulic fluid straight back out of the bottle with this enormous, unstoppable force. And that right there is the stored power that's going to race down the lines to crush those safety valves shut.
Let's zoom out for a second and look at how this fits into the overall safety layout. The accumulator unit is intentionally parked at ground level, deliberately set back at a really safe distance from the wellhead itself. I mean, you definitely do not want your emergency power source sitting right on top of the danger zone, right? Instead, this one unit feeds high-pressure lines out to 3 completely separate control points. You've got the driller's primary console up on the rig floor, you've got remote panels placed strategically along the crew's escape routes, and then lines going directly down to the BOP stack in the cellar. What that means is, if things go completely sideways, evacuating crews can literally just hit a lever on their way out and shut the well in while they're running to safety.
And there's some pretty strict math keeping this whole system in check. The American Petroleum Institute has a rule, API 16D. It basically dictates that the accumulator must hold enough fluid to close all the pipe rams, close the annular preventer, and open the hydraulic choke valve. Oh, and after doing all of that, it still has to retain 200 psi above the original nitrogen precharge. Because of this super strict requirement, you literally can't use every drop of fluid in the bottle. To put that into perspective, a standard 11-gallon bottle pre-charged to 1,000 psi really only gives you roughly 5 usable gallons of fluid. So you always have to calculate for usable capacity, not just total volume.
To really visualize how this behaves, I love this analogy. Think of the accumulator as a giant drawn crossbow, right? It takes this long, slow, grinding effort to pull the heavy string back and lock it into place. On the rig, that's the job of the electric or pneumatic pumps, taking several minutes to slowly charge those bottles up to 3,000 psi. But the release? The release is instant, and it is violent. When the driller pulls that lever, the crossbow fires. In under 30 seconds, that stored energy is going to slam the entire BOP stack shut against thousands of pounds of well pressure. But, just like a crossbow, once you've fired, you have absolutely nothing left until you slowly redraw the string.
Okay, so with all that immense power supposedly standing by, let me ask you something to test your intuition here. Imagine you're walking past the accumulator skid. You look down at the main pressure gauge, and the needle is resting perfectly at 3,000 psi. It looks totally full. Is your well actually safe? Are you absolutely guaranteed to have the power you need if the rig goes black right this second? Take a moment to really think about that.
Well, the answer?
is a massive no. You might not be safe at all. See, here is the silent trap. Nitrogen gas can leak, and it does so very slowly and completely silently. If your rubber bladder gets even a tiny tear, the nitrogen escapes. But the rig's pumps, they'll just keep shoving more and more hydraulic fluid into the bottle to make up the space until the gauge reads exactly 3,000 psi again. But now, your bottles are basically filled with solid liquid and almost zero gas. So when you pull that emergency lever, a tiny little splash of fluid comes out, the pressure instantly plummets to zero, and the valves don't even budge. You have a full gauge, but a totally useless system.
So, the absolutely crucial point here is this. A pressure reading does not equal stored capacity. Seeing 3,000 psi on a dial only tells you that the fluid is currently squeezed. It tells you literally nothing about the volume of that unseen nitrogen spring waiting behind it to do the actual pushing. The only way to know for sure that your well is truly protected is to physically shut off the pumps, bleed the hydraulic fluid down, and verify that the 1,000 psi nitrogen precharge is actually still intact. That's exactly why maintenance schedules require this physical check. If you aren't verifying the precharge, your safety device is nothing more than an assumption.
Let's pull all this together. The CUMI unit is, hands down, one of the most vital pieces of non-moving equipment on the entire rig. It stores incredible physical energy by squeezing nitrogen gas, and it acts as the ultimate fail-safe battery to power your blow-up preventers when literally every other system goes dark. And above all, it demands absolute respect through rigorous pre-charge checks, because trusting a pressure gauge without actually understanding the physics behind it, well, that can cost you the well.
Look, when you're dealing with millions of pounds of earth pressure and highly volatile gases, what you can't see is honestly just as important as what you can. So the next time you see a gauge reading completely full, whether you're out on a rig or anywhere else, I want you to ask yourself, are you trusting an assumption, or have you verified the unseen forces that are actually keeping you safe? Thanks so much for joining me for this explainer today, and remember to always keep questioning what's behind the dial.